Stiffness factor S. Stiffness factor means how much moment you have to apply so that rotation at that point is 1. That means moment required to produce unit rotation, we call it as stiffness factor. In springs also you have learned stiffness of a spring is load required to produce unit deflection. But in the case of beams, moment required to produce unit rotation. We call it as stiffness factor. Stiffness factor means it is the moment required to produce unit rotation. Case 1. When far end is fixed, stiffness factor S is equal to 4EI by L. This is what we have learned. What it means is, supposing that we have a beam like this, how much moment you have to apply so that theta B becomes 1, like this. I want theta B to become 1. For unit rotation, how much moment you have to apply? That moment we call it as stiffness factor, and that moment is 4EI by L. If you apply 4EI by L amount of moment, automatically theta B becomes 1. Why like that 4EI by L? How to know that? We will prove after this again with the help of moment area method. Next, case 2. When far end is hinged, stiffness factor S is equal to 3EI by L. This is what you have learnt. What it means is this one. When far end is hinged means this one. M. This is applied. We have to apply that much moment. Then the deflection profile will be something like this. A, B. For this theta B to become 1, your M must be 3I by L. That M we call it as stiffness factor, or in other words S is equal to, if you apply 3EI by L amount of moment, theta B becomes 1. Why you require less value of 3I by L? For fixed 4I by L, if it is hinged means only 3I by L. Because when you are applying moment, this also starts rotating. So this will facilitate to make theta B 1 quickly. So instead of 4I by L, you require less than 4I by L. That idea we should have, the feel of this structure we should have. Why you are getting less value? When you fix it, it is very stiff. To make theta B is equal to 1, more effort is required, 4A by L amount of moment. But if it is hinged, when you are applying moment, this is also rotating. So quickly theta B becomes 1. But that is at a value of 3A by L. This one you have already calculated in your strength of materials. This we have to derive. This we have already learned from SOM. What is that you have learned is this one. Assume that we have a simply supported beam. You apply a moment M, A, B. Then the deflection profile is like this. This is theta B. From strength of materials, you have studied that ML by 3EI. If you apply moment M, theta B is ML by 3I. That's what you have learned. Now, stiffness factor means stiffness factor S is equal to moment required to produce unit rotation. I want theta B to become 1. Then how much you have to apply? See here, for theta B is equal to ml by 3ei, you have to apply a moment m. For theta B is equal to 1, how much moment you have to apply? Yes. So less value. So less by more value. So S is equal to 1 by theta B. That means 1 by ml by 3i into m. So 1 by theta B means 3i by L. Or you can write mb by theta B. mb by theta B is ml by 3ei. So finally you will get 3ei by L. The derivation of this is like that. In strength of materials, you have stopped here itself. How much moment you have to apply? You applied, and then what is the slope? ml by 3ei. There you stopped the work. Now the extension in the structures. That m by theta, if I want theta b to become 1, whatever moment you apply, that we want to call it as stiffness factor. Okay. So that's how it comes. Next, case 3. Supposing that if you have, once they asked this 2 marks question, moment required to produce unit rotation is. Instead of m, they have simply given k. K is how much? K is how much? So that the deflected shape is like that. I want theta b to become 1. Theta is equal to 1. Here also I want theta is equal to 1. Then how much k you have to apply? For moment m, this what you have studied. If you apply m, deflected shape is like this, and this is theta a, ml by 2ei. This what we have learnt. Now stiffness factor k means moment required to produce unit rotation. So m by ml by 2ei. So you will get 2ei by L. So if you apply 2ei by L amount of moment here as well as here, then theta becomes 1 as well as here, like that. Okay. Now that's how the questions will come based on the deflection profile from strength of material. All the formulas generally from the strength of materials only we will get it. We don't have to derive anything extra. We cannot derive and give the explanation. The things that you have already studied will be given 20-30 seconds. You can complete the problems. Now let us see the fourth case, cantilever beam. See here in this case 4a by L, here 3a by L, here 2a by L. It can be ei by L also. Those values depend on the support conditions. Okay, that we'll see now the fourth case. Case 4. For cantilever beam, when moment is applied at free end, stiffness factor S is equal to simply EI by L. Why like that? This is what we have learnt. When you apply a moment M, the deflection profile is like this. This is the MB, let us say. Then this is theta B. We know the formula ML by EI. Stiffness factor means moment required to produce unit rotation M by theta. So M by theta is ML by EI. Why M by theta? I told you. One biscuit is 2 rupees. 3 biscuits how much? From that only you can get. Okay. This is for moment. S means moment required to produce unit rotation. For theta rotation, if you know how much moment, for unit rotation, how much? Just linear interpolation. So you will get EI by L. Next, so is the case with the case 5. When far end is guided roller support, stiffness factor S again is same. This I have already explained to you because the deflection profile is like that. This point, let us say A, B, M. For this theta to become 1, moment M is EI by L. If you apply EI by L amount of moment, automatically theta becomes 1. So this is about the stiffness factors. It can be 4, 3, 2, 1. It can be 0 also. Now let us see under what circumstances moment required to produce unit rotation can be 0 also. With 0 moment, why it will rotate by unit amount? Let us see that case. Case 6. When far end is free, stiffness factor S is 0. Now this cantilever beam case, you cannot say far end is free. This MB is equal to M, we have to apply, this is we applied. In this case, this is your applied moment. This applied moment must be EI by L. Since you are applying here, we are here. We are here and applied. So this is not a far end. Far end is this one. So if at all moment is applied somewhere here, when far end is free, when far end is free means that cannot come to this one. Let us see when how the far end is free looks like. Assume that we have a fixed support here. This is some hinge support. This is the beam. This point, let us say A, B, C, D. Okay. Now you apply a moment M here. This is M. This is applied moment. You are applying moment at the rigid joint B. That means applied moment means you are here. Now for you this is far end. Such far end, if it is free, its stiffness factor is 0. That means with 0 moment itself, why should it rotate by 1? Let us see the deflection profile. When you apply a moment M like this, how the deflection profile is? Hinge supports means it will bend like this. Now, well, to maintain the 90-degree angle, it has to go like this. If you drop tangents, if this is theta B, let us say, then these are all members rotate by the same angle. 1. This is the tangent. Again, one more. We see angle between the tangents after rotation also 90 degrees maintained. Rigid joint is a joint where angles between the members will not change after applying the moment. At such rigid joint, if you apply a moment M, then when far end is free and for that member stiffness factor means moment required to produce unit rotation is 0. Now, why it is 0 is because of this reason. You applied a moment M. What is the because of this M? These two members bend, but this one will not bend, but it will rotate. What is the difference between that? Bending means it deforms after bending. Without deformation, if it bends, we don't call it as bending, it rotates. Rotation, we call it. Now you see, even if you apply M value 1000 ton meter, BD member bending moment is how much? Stand here, look one side. I will not look left side, I will look right side. So here it is 0. That means bending moment in the member BD is 0. Whatever may be moment you apply. For any member to be under tension, you require two forces. To be under compression, two forces. If you want any member to bend, you require two moments. With one moment, you cannot bend any member. It will rotate as a rigid body, but it will not bend. So bending moment is 0 in this member because of this free end. So freely it will rotate. It's like this. Supposing that you have a fixed support here, here some hinge is there, then I have to apply some effort, then only it will rotate. When I am applying a moment here. Now I don't apply moment here, this is the cantilever beam, this is the support. On the support, I apply moment like this, suppose support rotates due to some reason say. See see when I am rotating like this fellow, why only one rotation? 180 degrees also I can rotate with 0 moment. But if I hold this one, then if I rotate means it will, you require some effort, then only it will bend and rotate. But if it is free, freely it will rotate like this. If I apply here a moment, freely it will rotate. Okay. Now if such cases, when far end is free, at this point when you apply moment, this offers 0 resistance for unit rotation. As a rigid body, it will rotate. That is the case here. When far ends are free, then moment required to produce unit rotation for this member is 0. Because MBD is 0. Whatever moment M you applied, these two members only will take. This fellow says I cannot take. But because you have rigidly connected, that will also rotate. It will rotate, that's all, without offering any resistance. Okay. So D is, we'll write here. Far end D is free. So BD will not bend. That means bending moment in BD is equal to 0. So BD as straight line, remains as straight line. Straight line, as a straight line, it will as a rigid body rotate. That is not a bending deformation. So stiffness factor is 0. This is the case we are discussing. Now, 6 cases we have taken. Stiffness factor we have learnt. Now let us see what is the relative stiffness. That we'll see the concept number 4. Relative stiffness factor, or simply relative stiffness, that's all. Relative stiffness K. Relative stiffness means it is a relative value of the stiffness factor. It is the relative value of stiffness factor. Then why we define such relative values is just to simplify our calculations. It is defined to simplify our calculations. What calculations we want to simplify? In the next concept, we will get a concept called distribution factor. There you will get stiffness factor by sum of the stiffnesses. There we remove that stiffness factor 4E by L by as E by L, as I by L. Its relative values we will write, so that unnecessarily writing 4E by L plus 3I by L in the denominator also, again 4E by L will come, cancel it out. Instead of unnecessarily writing and cancelling and wasting the time, you directly write the relative values like this. Case 1. When far end is fixed, relative stiffness K is equal to I by L. So, stiffness factor, relative stiffness. First one, relative stiffness, if you have, say, if S is equal to 4EI by L, you will write K as I by L. So 4EI by L, you are writing it as I by L. Then case 2, when far end is hinged, relative stiffness K. How much we should write? See here, this you assume that 4 biscuits. 4 biscuits is equal to 1 rupee. Now 3 biscuits how much? If S is equal to 3 EI by L, how much K I have to write? This is similar to like this. 4 biscuits are 1 rupee. 3 biscuits how much? 3 by 4 rupees. If 4 EI by L, if you write it as I by L, 3 I by L, how much you have to write? That's all. 3 by 4 I by L. So 4 biscuits 1 rupee, 3 biscuits how much? 3 by 4 rupees. So K value will become 3 by 4 I by L. That 3 by 4 comes from that simple reason only. Okay. If you know this quantity, 4 biscuits is so much, 3 biscuits how much? 50% of strength of materials is over, I told you. Here also almost same concepts will run. Where you get stuck up such concepts, this will clear our doubts. Next, case 3. For cantilever beams, when moment is applied at free end, how much is now relative stiffness will become is relative stiffness K is equal to, you have to write 1 by 4 I by L. Why? If stiffness factor is EI by L, what is the relative stiffness? We have to write K is equal to 4 EI by L. If you write I by L, EI by L, how much we should write? 1 by 4 I by L. So is the case here, case 4. When far end is guided roller support, same case now, relative stiffness. Relative stiffness K is equal to 1 by 4 I by L. Next, last case if I take, this also same as the earlier one. Supposing that if I take, when far end is free, then what should be the relative stiffness? K value. Now you see here, when far end is free, relative stiffness I told you, stiffness factor I told you 0. Then what should be the relative stiffness? Also 0. If 4 biscuits 1 rupee, 3 biscuits 3 by 4 rupees, 0 biscuits how much? 0 rupees. So if stiffness factor is 0, relative value also must be 0. So just to simplify calculations, these relative stiffnesses are defined. Now let us see the fifth concept, distribution factor. Distribution factor means at a joint, 4 or 5 members are meeting, let's say. When you apply a moment M on the rigid joint, then all members will share your applied moment. In what ratio your applied moment gets distributed to the members meeting at that joint, that ratio we call it as distribution factor. It is the ratio in which the applied moment is distributed distributed to various members meeting at a joint. Meeting at a rigid joint. Let us see why that rigid joint specification. What it means is, assume that there are so many members meeting. This point, let us say A, B, C, D, E, F. So 1, 2, 3, 4, 5 members are meeting at C, and C is a rigid joint. Rigid joint means angle between the members before, after application of the loads remains same. So now when you apply a moment M, this M is applied. You went and applied this much moment. There is a difference between applied moment and reacting moment. Applied moment is what we apply. Reacting moment is what is developed or what is given by the support on the beam to keep it in stable condition. Okay, when you apply moment M, because it is a rigid joint, all members rotate by the same angle. That's the meaning of rigid joint. Assume that because of M, these members rotate like this. All should rotate by the same angle. Blue colored one is the deflection profile after applying the moment. This angle, let us say theta. This is also theta. Theta here, this is also theta. So all will rotate by the same angle. Then in what ratio this moment gets distributed? Your applied moment, this will take 20%, 30%, 0%, 5%, like that say. Then that ratio, we call it as the distribution factor. When you apply moment M, the stronger members will take more moment. Weak members will take less moment. Who will tell you whether who is strong member or weak member? That stiffness factor will tell us who is strong, who is weak. That means, is it easy or difficult to rotate a member by theta? If it becomes difficult, say, that means stiffness factor is more, say, then very difficult to rotate, then its share of our applied moment is also more. Like in the one example I told you in the axial, supposing that in a room, two members are there. You give 10 rupees, one fellow is very strong, one fellow is weak. Strong fellow will take 80% of the 10 rupees, that means 8 rupees, he may give only 2 rupees. Sometimes if he is so weak, he will not give any money at all, like free hand, like that. So their muscle strength will decide who will take more moment, who will take more money or less money. Here, stiffness factor will decide who will take more moment, who will take less moment. If they are axially loaded, axial stiffness will tell us who will take more applied load, who will take less applied axial load. So axial stiffness, flexural stiffness's purpose is that is it easy or difficult to translate or to rotate a member? Okay, so this is the thing. Stiffness factor S decides the flexural strength of a member. So stiffness factor S is a measure of flexural strength of a member. If S is more, stiffness factor is more, then its share of applied moment, is also more. So now your distribution factor means what is the stiffness factor of a single member by sum of the stiffness factors of all the members. In that ratio, your applied moment gets distributed. Now, stiffness factor 4A by L, here also 4A by L, 3A by L, then 4E, 3E, cancel it out. Instead of that, you write the relative values, K by sigma K. The question of cancelling will not be there. Okay. So, only here we use that stiffness factor. You write in terms of relative values just to simplify the calculations. 4A by L here, 4A by L plus 3A by L, then 4E, 3E, you have to cancel it out. Instead of that, you write relative values, no cancellation. That's it. Okay. Now, this type of distribution we have learned in strength of materials also. This example I have already given you. You apply load P, let us say. This is L by 2, L by 2. This axial rigidity AE, this is a 2AE. If both of them are equally strong, sir might have told you 0.5P, 0.5P. If this is axial rigidity is doubled, then load carrying capacity P by 2 will not be doubled, P will not come. So it will slightly increase. Maybe this point, let us say ABC, you found that HB, let us say 0.8P. Then this will become 0.2P. That means out of P, this will take 20%, this will take 80%. That's how it will share. Then who will decide who will take more load or less load? First chapter, strength of materials, this what you have learned. Axial stiffness. What is axial stiffness? AE means axial rigidity per unit length is called axial stiffness. Axial stiffness decides axial strength. Decides axial strength of a member. If AE by L is more, then its share of applied axial load is also more. Okay, this is what you have learned. Their axial stiffness, if you remember the problem, strength of materials problems, if you see AE, central load you apply, say, then 0.5P, 0.5P you might have got. Then next problem sir might have told you, one is AE, one is 2AE. Then here reaction is more. If not 0.8P, maybe say 0.75 or 725 or 735, some value I am telling you just slightly more than 0.5P. So 0.8 let us say, then 0.2 here. That means reaction increased. That means what? CB member is subjected to a compression of 0.8P. AC member is subjected to tension of 0.2P. So tensile force is less, compressive force is more. That means its share is more. Who decided that? This one, AE by L. Not just axial rigidity, by length. Together, AE by L term will decide who will take more or less. Here, yes, 4EI by L. 4EI by L or the stiffness factor will decide whether it can take more moment or less moment. So whether it is strong member or weak member, that stiffness factor will decide. If stiffness factor is very, S value, 4EI by value is very high, that means moment required to produce unit rotation is very high. That means member is very strong, very difficult to rotate the member. Okay. So in that stiffness ratios, they will share. the applied moment. Okay, that's the reason why distribution factors are defined. In what ratio your moment gets distributed. There two members are there, here five members are there. Or it can be four members only, or three members only, whatever may be that. In that way, it will get the stiffness factor tells you in what way it should get distributed. Okay, so this is distribution factor. Next, second point is I have written here rigid joint only. What happens if there is a pin joint at C? If you have a rigid joint and we apply moment, all members rotate same angle, then you will know who will take more moment, who will take less moment. If there is a pin here, all five members are connected by a pin. On the pin, you apply say 10 kilonewton meter. So entire 10 kilonewton meter pin only will take, and pin will rotate like a shaft. That pin will not transfer any moment to any member. All members simply keep quiet. So distribution factors are defined for all members meeting at a rigid joint only. At pin joint, the distribution factor concept itself will not exist. It will not distribute at all. So distribution factors are defined for members meeting at a rigid joint only. Defined for members meeting at a rigid joint only. If there is a pin joint at C, if there is a pin joint at C and moment is applied, then it will rotate, and will not transfer any moment to any member. That's why we say that distribution factors are defined for members meeting at a rigid joint. Now, then what is the rigid joint? This point I think I have completed. Third point is what is a rigid joint? Rigid joint is a joint where angles between the members remain same after application of the loads. Remain same after application of the loads also. Next, fourth point is sum of the distribution factors. Out of this M, S by sigma S, first member S1 by sigma S, say 0.2, S2 by sigma S, say 0.3. Like that, S1 by sigma S, like that if you write it. Sigma S by sigma S you will get if you sum them. That means 1 you will get. It took 20%, 30%, 0%, 20%, 30%. What are the percentages of all that? 100%. That means 1. So, sum of the distribution factors, SUM, sum of the distribution factors of all members meeting at a rigid joint is 1. Sum is 1. Next, fifth point is this one. If at all the far end is free, say this one, if stiffness factor is 0, distribution factor also 0. That's the fifth point. If at that far end free, if far end is free, first I told you stiffness factor is 0, relative stiffness is 0, that means distribution factor is also 0. If you come to here, for member CF, CF means far end is free, its stiffness factor, relative stiffness, distribution factor, all of them are 0. Okay, now these are the 5 points: carryover moment, carryover factor, stiffness factor, relative stiffness, distribution factor. These are the 5 points on which most of the indeterminate structural analysis depend. So that's why every year one question compulsorily will come from these 5 concepts. Okay, so now we'll see why the carryover moment is m by 2 in the first case when far end is fixed. We will take the help of moment area method. So first we'll briefly review what is moment area method and how to get those values. If those fundamentals are clear, then further we can go ahead confidently. Concept 6, moment area method. Now in the when you have used moment area method is, there are various methods: moment area method, conjugate beam method, double integration, strain energy method. But out of all the methods, you will use moment area method when finding area of BMD, finding the CG of area of BMD are simple, then moment area method you can complete in 1 minute time itself. All the deflections you can complete so fast. That's why we are taking the help of moment area method. If finding area of bend moment diagram and CG of area of bend moment diagram are simple, then this method is used. Then this method is used to find slopes and deflections. Slopes and deflections in beams quickly. Okay. Now, in that process, you have learned about Morse theorem 1. What it tells you is theta is equal to A by EI. What is that theta? Is this one. Assume that we have a simply supported beam subjected to some general loading. A, B. The deflection profile of this beam is like this. Okay. And the bend moment diagram will go something like this. Now at A, if you drop a tangent on the deflection curve, it will cut the vertical line somewhere B dash, let us say. At B also you draw one more tangent to the deflection curve. Assume that it goes like this. It will cut somewhere here. This slope, let us say theta A. This slope, let us say theta B. From Morse theorem 1, you get theta. You don't get theta A or theta B. Which theta you will get? Angle between the two tangents. At A you have drawn one tangent. At B you have drawn another tangent. What is the angle between the two tangents? If you drop, say like this. If this is theta B, this is also theta B. If this is theta A, this is theta A. This theta you will get. That means theta is nothing but theta A plus theta B. So you will get angle between the two tangents drawn on the elastic line. This blue color line we call it as elastic line. What's the other name? Elastic line or deflection curve. Both mean the same. So what it tells you is the angle between the two tangents drawn on the elastic line, that is theta, is given by area of the bending moment diagram between those two tangents. This is the total area, let us say. Between the tangents means at A, B you have drawn two tangents. So between A and B, what is the area of the bending moment diagram? That area of the bending moment diagram divided by EI will give you theta directly. Angle between the two tangents you will get. So we'll write that statement. From Morse theorem 1, you don't get theta A or theta B. You will get sum of the two angles. Theta A plus theta B as theta you will get. So this is theorem 1. It states the angle between two tangents drawn on the elastic line is given by area of BMD between those two tangents divided by EI, that is theta is equal to A by EI. Next, what is Morse theorem 2? Theorem 2 tells you this is Morse theorem 2. From Morse theorem 2, you don't get the beam deflections at all. Now you see, assume that you have a small string. One end of the string you hold it here, other end of the string is B dash. So A string, this is B dash, A B dash straight line. Now hold the string at B dash and lift it like this. Then this red color dotted line will lift up, it will take a blue color shape. For clarity's sake, BB dash we have given so big. Actually, it is very small. This length is in meters, say. This is 0.001 radian like that. This is in terms of mm. So compared to this length, this is very small. Why? Because this theory, whatever you have studied in strength of materials, deflections theory is applicable only to small deflections. Large deflections are there, all those formulas are not valid. Okay? For small deflection theory, beginning itself eid square y by dx square is equal to minus m when you are writing, you assumed that they are applicable to small displacements only. Okay? So this bb dash actually it is a curve, arc. AB rotated. So BB dash is like an arc of a circle. But because very small, you took it as a straight line. So these are very small. If I draw a tangent like this, most of you cannot see that BB dash. So I pulled it so much down. What it tells you is take a string, hold it, hold this B and lift it. So BB dash is the deviation of point B away from the tangent drawn at A. That means at A you have drawn a tangent, how much that B dash deviated from its original position. That deviation you will get from Morse theorem 2. BB dash is equal to, that means delta is equal to BB dash is equal to AX bar by EI. That means if you want to find BB dash, this is the area of the bend moment diagram say. CG is somewhere here, this distance let us say X bar. Area into X bar by EI, you will get this deviation, not this deflection. Okay. So, theorem 2, it states the deviation of any point B away from the tangent Now see, this says the deviation of any point B away from the tangent drawn at A is given by moment of area of BMD about B divided by EI, that is delta is equal to BB dash is equal to AX bar by EI. Supposing that if you want to find this deviation, from here you have to measure centroidal distance. If at all you want to find A dash say, that means BA dash is the tangent drawn at B and this is the deviation. Hold it, lift it. So A dash. Then if you want a deviation of point A away from the tangent drawn at B, then moment of the area about A we have to calculate divided by EI. That's what you have studied. Now this is the revision. Now let us see if at all to find theta A, which theorem we have to use first? Not Morse theorem 1. Morse theorem 1 gives you this theta which is useless. First you have to find BB dash. Then this length let us say L. L into theta A is equal to BB dash, like R into theta. If this is the radius R, this is theta, arc length is R theta. If theta is very small straight line. So using Morse theorem to first find this one, R theta means BB dash. Then theta A means BB dash by L. Okay. So to find theta A, first find BB dash using Morse theorem 2. Then L into theta A is equal to BB dash. Now theta A you will get BB dash by L. Okay. This much fundamentals, whatever you have learned in strength of materials, I think now you have recollected. Now let us apply these concepts to our problems. How to find the carryover moment and how to find the stiffness factor. Now let us see the questions. Prove that carry over moment is equal to m by 2 when for end is fixed. This is our problem. How that m by 2 came, we want to know. This is mb is equal to m. This is, let us say, applied moment. This point, let us say A, B, L. The deflected shape of the beam is like this. Okay, we know that here theta A is 0, MA we have applied. Okay, now you see bend moment diagram we will try to draw. You assume this propped cantilever as a simply supported beam. First you apply MB alone, then bend moment diagram we know how to draw. Plus M. This is bending moment diagram due to M alone. That means assume this fixed you removed. You took it as simply supported beam. This beam is similar to a simply supported beam subjected to a moment M and simply supported beam subjected to a moment MA. If both bend moment diagrams you add them, you will get a propped cantilever bend moment diagram. Principle of superposition. So due to M alone plus now simply supported beam subjected to hogging moment. This also we know how to draw bend moment diagram. Is another triangle minus this value is MA. We want to know how much it is. This is bending moment diagram due to MA alone. So plus we are writing, this is because of from the principle of superposition. Principle of superposition, you can add the two bend moment diagrams. What we have done actually here is like this. This is a simply supported beam, let us say AB. Apply M alone. For this bend moment diagram is like this. Next, plus take another beam. Apply MA alone. For this bend moment diagram is like this, hogging bend moment. So M and MA on this beam, if you take this and stick it, then you will get this one. That means if you add these two bend moment diagrams, you will get final bend moment diagram. Why should we split them like this and waste our time? We could have drawn directly negative to positive, we could have written. Then you must know where is point of conflexure. Then you must know centroid, area, lot of time waste. But if you take MA, M and MA separately, this triangle area easy, finding CG simple. In moment area method, you must draw bend moment diagrams such that its area centroid must be found easily. Then it can be completed in 1 minute time itself. That is advantage of moment area method. So to take the advantage of moment area method, we split the bend moment diagrams where each bend moment diagram is easy to manage. So now you see, if at all theta A is not 0, supposing that theta A is existing, then the deflection profile could have been something like this. BB dash. So it will deflect like this. Theta A also will be there. What is theta A actually? BB dash by L. In this case now theta A is 0. That means BB dash by L must be 0. That means BB dash must be 0. So that is called compatibility condition, a relationship between the deformations. See here, from compatibility condition means a relationship between the deformations. Known deformation it is. From compatibility condition, theta A is equal to BB dash by L is equal to 0, which means that BB dash is equal to 0. If what is BB dash? From Morse theorem to AX bar by EI must be 0, which means that AX bar must be 0. Area into X bar must be 0. Otherwise, theta A will not be 0. Now, what is area into X bar? First area will take this one. This is the centroid. X bar you have to measure from B, L by 3. This is again CG. This is X bar. This value is 2L by 3. Okay, area into X bar, area into X bar with due signs for plus and minus. First black color one, positive area, half base into height, MB, into X bar is L by 3. This is positive area plus negative area minus half base into height into X bar 2L by 3 must be 0. So MB into L square by 6 minus MA into L square by 3 must be 0. So MA you will get MB by 2 is nothing but M by 2. So to make theta A 0, your MA must be M by 2. Conclusion. To make theta A is equal to 0, MA must be equal to M by 2. So that's how the carryover moment M by 2 came. Now, if you see the stiffness factor, this I think is done. We'll remove this point. Next point is this one. Prove that stiffness factor S is equal to 4 EI by L when far end is fixed. Now see, it runs now because we are proving the stiffness factor. MA M by 2 directly will write. This is M. Again, applied moment. This point let us say A, B. Length is L. Now the deflection profile will go like this. Here MA we know. Now we will not prove why it is M by 2. So bend moment diagram due to M alone will go like this. M. This again same problem, we don't have to again write the same. Plus bend moment diagram due to MA. It's negative minus. This value is MA is nothing but M by 2. Okay. Now, here you drop a tangent. We wanted this theta B as 1. This is a dash. Now, how much moment M we have to apply so that theta B becomes 1? We have, it is actually 10 marks question. You can complete in 1 minute time. Now you see, theta B if I want to find, I can use A dash by L. Supposing that A dash means AX bar by EI you have to write. Even that time also you don't want to waste say. I can take Morse theorem 1 also directly. Morse theorem 1 tells you the angle between the two tangents drawn on the elastic line gives you area by EI. So one tangent at B you have drawn, this is the red color line. Another tangent you draw at A, that will go like this because slope is 0 here. So this tangent drawn at A is this. Tangent drawn at B is this one on the deflection curve. So angle between the two tangents directly theta B you will get because theta A is 0. Earlier theta is nothing but theta A plus theta B. If theta A happens to be 0, theta becomes theta B only. Actually angle between the two tangents is theta. Angle between two tangents drawn at A and B is equal to theta A plus theta B is equal to A by EI. In this case theta A is 0. So theta B you will get A by EI directly. Only when theta A becomes 0, theta B gives you more, you can get from Morse theorem 1. So theta B. What is the positive area? Half base into height by EI. This is positive area plus negative area minus half base into height by EI. So this is this value will get ml by 2 EI minus ml by 4 EI. So you will get theta B is equal to ml by 4 EI. This value you have to remember. So much standard case that theta B that we have to remember this value. We cannot, though it's a one line derivation, that one line also we should not derive and get the value as ml by 4 EI. So fundamental it is. Not only here, wherever you see this type of deflection profile where deflection is 0, slope is 0 here like this, wherever you see in that segment, I can write theta B as ml by 4 EI. Okay. Now stiffness factor S is equal to mb by theta B. mb means m, theta B is ml by 4 EI. So you will get 4 EI by L. Supposing that this idea you didn't get, angle between the two tangents. You got the idea that first I'll find theta B as AI dash by L. Then also same time only 20-30 seconds extra time you have to spend. How it should be done is like this. Second method, theta B is nothing but A dash by L. A dash means AX bar by EI. Then AX bar. Because you are finding A dash, area into X bar you have to measure from here. This is CG, let us say. X bar you have to measure from here. This X bar is 2L by 3. For this one CG is here. This is your x bar. You will get L by 3. So area into x bar, area into x bar. So positive area is half base into height. Area into x bar, black color triangle is 2L by 3. Ax bar by EI plus negative area minus half base into height is m by 2 into x bar is L by 3 by EI. So you will get this is ml square, 2 cancels out, ml square by 3 EI minus ml square by 12 EI. Common factor is 12, 3, 4, 4 minus 1, 3, 3 by 12 is 1 by 4. So ml square by 4 EI. Now A theta B is nothing but A dash by L. That means ml square by 4 EI by L. Same formula. Only thing is area into x bar terms you have to little bit 15-20 seconds maybe extra calculation you have to spend. Otherwise directly we can get it area. So that's where you have to, that means there is a choice of writing A dash by L. The deflection profile will tell us whether to use Morse theorem 1 or Morse theorem 2 to find the slope or deflection. Okay. So this in a propped cantilever beam, slope at the propped end due to a moment is ml by 4ei. That we are expected to remember because many places we use in matrix methods also we use this one. So we should not derive this only one line derivation only, but you have to draw this diagram, then this derive. That much time you cannot afford in the exam. Okay. So now let us see when far end is hinged, stiffness factor is 3i by L. So that formula, how we will get it is like this. Prove that stiffness factor S is equal to 3 EI by L when far end is hinged. This again strength of material sir might have told you already. I will just revise how you have to get it. This is your M, applied moment. How much you have to apply so that theta B becomes 1 is the aim. Like this it deflects. Now two bend moment diagrams are not there because there is no MA here. It is simply that's all, M. This is only bend moment diagram. Now angle between the two tangents you cannot find because theta A is not 0. This problem you have no choice. To find theta B, you must use A dash by L only. Morse theorem 1 you cannot use it because theta A, if it is 0, then Morse theorem 1 directly gives. But theta A is not 0. If theorem 1 gives theta A plus theta B. So we should not use Morse theorem 1. This second method only you have to use. So theta B is equal to A dash by L. Then A dash is equal to Ax bar by EI. X bar means this one. This is the bend moment diagram. So centroid is here. X bar is this one. This you have to calculate, not this one. So x bar is 2L by 3. So area is half base into height into x bar is 2L by 3 divided by EI. So 2 cancels out. You will get ml square by 3ei. Now theta b is equal to aa dash by l. So ml square by 3i means now it will become ml by 3ei. These words are derived in strength of materials about the theta b. Wherever you apply moment m, at that point in a simply supported beam, slope is ml by 3ei. That's what you have studied. This to be remembered. Then stiffness factor S is moment at B by theta at B only. So M by ml by 3ei. So you will get 3ei by L. That 3i by L comes like this. SM sir might have told you what is theta A also. ml by 6ei. Supposing that you have forgotten. To get that is only one line derivation. You see here, we want to know what is theta A. Drop a tangent, BB dash. This is a theta A. What is theta A? BB dash by L. See here, that in case we require, that means those formulas how easily we can find using Morse theorem. To find theta A. So theta A is BB dash by L. BB dash means A x bar by EI. Now x bar, BB dash when you are finding, x bar you have tried from here. This becomes L by 3 for this problem. So area is half base into height. X bar is L by 3 by EI. So you will get ml square by 6EI. Now what is theta A? BB dash by L. That means L will be gone, ml by 6EI. Okay. This is also to be remembered. Like that. So these are the fundamentals on the moment distribution method, how the values come. Now based on this, how Hardy Cross has given his moment distribution for the beams we will see. But before that we will see what are the how the fixed beams, the fixed end moments are calculated. That also we will discuss. So we just revise what how the values will change, because we use the fixed beams moments also in the moment distribution method. Okay. Now we have discussed the till now 6 concepts: carryover moment, carryover factor, then relative, the stiffness factor, relative stiffness, distribution factor, and moment area method. And using moment area method, how to find the carryover moment? You found that it is m by 2. When far end is fixed, stiffness factor also we found it is 4a by L. Now same moment area method, we will use it for fixed beams to get certain expressions, to get the fixed end moments, so that those fixed end moments we use it for our moment distribution method. Now 7th concept, fixed beams. First one is fixed beam subjected to central point load W, L by 2, L by 2. This point let us say A, B. For this one, we know the deflection profile. At the fixed support, slope will be 0. You found that MA is equal to WL by 8. MB is also WL by 8. Assume that you have forgotten that it is WL by 8. We want to derive, or we want to analyze the fixed beam, let us say. First what we do is, We assume or we make the structure a statically determinate beam. That means remove the end moments. MA and MB, you remove them. When you remove it, fixed will become like a simply supported beam. Once you release the fixity, fixed support will become like a simply supported beam. Compared to simply supported beam, fixed beam, what is extra? Moment. Remove that moment, it becomes a simply supported. So for a simply supported beam, subjected to central point load, we know how to draw the bending moment diagram. This is WL by 4, positive bending moment. This is bending moment, free bending moment diagram, we will call it. This is called free BMD. Free BMD means bending moment free from whom? Free from end moments. So bending moment diagram free from end moments. That is bending moment diagram assuming the beam as simply supported beam. This is a free bending moment diagram. So like this first you have taken. First you are taking it as a simply supported beam subjected to central point load. For this one we know the bending moment diagram is like this. WL by 4. But this and this are not same. Next what we do is we apply the end moments. Here it is MA, here it is MB. Okay. Now if these two bending moment diagrams or these two loadings, if you add them, simply supported point load W, simply supported subjected to end moments, those two loading diagrams, if you superimpose, then you will get the fixed beam. Now this is equal to this plus this. Now when a simply supported beam is subjected to two end moments, we know how to draw the bending moment diagram. It's like this, MB and MA. For this one, this is the bending moment diagram. For this loading, this is the bending moment diagram. This is positive, this is negative. So that is called, how can we write like that? From the principle of superposition. How can you apply principle of superposition? Because the material is linear elastic and the deflections are assumed to be very small. The cross-sectional configurations, they don't change for small deflections. Large deflection means then the cross-section also will change. Initially say 10 mm diameter, when if it deflects 1 meter, 10 mm diameter will become maybe 5 mm like that. Where cross-section changes because of the large deformations, you cannot apply principle of superposition. Two conditions: material must be linear elastic, deformations must be small, otherwise you cannot apply principle of superposition. Okay, now only two end moments you take it. Plus, if you take the end moments diagram, minus this value, we are taking that WL by 8, WL by 8. This is bending moment diagram due to fixed end moments alone, due to fixed end moments alone. But since two loads are there on this structure, you add them. From the principle of superposition, add the two diagrams, you will get final bending moment diagram like this. Positive, negative. Both diagrams you write it on the same side. If you write positive area of BMD, negative area of BMD on the same side, positive area and negative area, if they overlap, cancel them. The area that didn't get overlapped is your net bending moment diagram. So negative area didn't get overlap. Here positive area didn't get overlap, negative area didn't get overlap. This value we have taken WL by 8, WL by 8. Now this value will become, total height is WL by 4. That means this side is WL by 4 minus WL by 8. So you will get WL by 8. So this is your final bending moment diagram. So fixed beams are analyzed this way. This is final bending moment diagram. How you got this one? From the principle of superposition. Okay, now let us see these points. Note 1. Assume that you have forgotten that MA and MB values. Then what we do is this one. To find MA and MB, we take the help of Morse theorem 1. What is Morse theorem 1? Angle between the two tangents drawn on the elastic line is given by area of the bending moment diagram between those two tangents divided by EI. Now, what is the angle between the two tangents drawn at A and B? At A you drop a tangent, it will go like this. At B you drop another tangent, it will go like this. What's the angle between them? 0 degrees. Not 180 degrees, it is 0 degrees. So, we can write like this. From Morse theorem 1, theta is equal to angle between two tangents drawn at A and B is nothing but A by EI, nothing but 0. That means positive area by EI plus negative area by EI, sum must be 0. Otherwise theta will not be 0. Means angle between the two tangents will not be 0. That means positive area of bending moment diagram divided by EI plus negative area of bending moment diagram divided by EI must be 0. When the sum will be 0? When both A by EI values must be equal. That means positive area by EI must be equal to negative area by EI. Negative area by EI. Then sum will be 0. So that means due and once you put it on the right side, again minus we should not put it. This plus, actually plus into minus is minus. So that sum must be 0. Then it goes to the right side, means it will become now negative area. Magnitudes only we have to take. This is a characteristic of any fixed beam. Any fixed beam where slopes are 0 at the supports, this is valid. Whether EI values are constant or different. Some portion may be EI, some portion may be 2EI, some portion may be EI, whatever may be the case. Positive area by EI must be equal to negative area by EI. Okay. Now, if at all EI is constant, if EI is constant, positive area of BMD must be equal to negative area of BMD. Areas themselves will be equal because EI is constant, means you can strike it off. But if not constant, you have to calculate separately. In this case, positive area means, you see here black color bending moment diagram, half base into height. Negative area is MA into L. Its value we have already written, but if not MA or MB, we could have written. This value is actually MA. This is MB. both values they have to be same. So now we can write it as positive area is half base into height WL by 4 must be equal to negative area. I can write MA into L or MB into L. Because of symmetry, MA and MB must be equal. So instead of two unknowns, only one unknown it became. So we can write MA is equal to MB is equal to WL by 8. So if you equate positive area and negative area, you will know how much should be the fixed end moment. It will be simple cases we get like this. In 2 marks questions if they give, maybe you have to spend around 30 seconds time to know what is the fixed end moment developed. Okay. So this is the first observation. Second observation, if you see, maximum positive area, maximum negative area or maximum positive ordinate, maximum negative bending moment are equal. Number of POC, this is a point of contraflexure. This is also point of contraflexure. So number of points of contraflexure are 2. POC means points of contraflexure are 2. Maximum positive bending moment, maximum negative bending moment are equal. That is your second point. Maximum positive bending moment is equal to maximum negative bending moment is equal to WL by 8. Why these values are also important for is this is only elastic analysis. That means when the load is applied, it will deflect. If you remove the load, this blue color line will swing back to its original position. So that is called elastic analysis. Deflections are elastic. Loads are applied within the proportionality limit. If the load is removed, the beam will bounce back to its original position. That is one analysis. Now, later on in the design of steel structures, that is based on plastic analysis. And plastic analysis means aim of that plastic analysis is at what load the structure collapses. That means after elastic analysis is over, you continue to load till it completely collapses. Their collapse means not completely breaking into pieces like a powder form and falling down. Collapse of a structure implies that the structure will become unstable or a mechanism. Due to the applied load, if mechanism forms, then the load we call it as collapse load. Mechanism means rigid body translation or rigid body rotation. Due to the load, if the structure undergoes rigid body translation or rigid body rotation, we say that the structure collapsed. Collapsed means it became a mechanism. Corresponding to that mechanism, how much load you have to apply? That load we call it as collapse load or failure load. Now, when you are go on increasing the load, plastic hinges will develop. Plastic hinges means the bending moment capacity reaches its plastic moment capacity. Then what will happen? The cross section will rotate like an ordinary hinge, which we call it as plastic hinge. In the plastic analysis, again I'll explain in detail, around 20 hours like that we'll spend on plastic analysis of beams and frames. This is now we are in elastic analysis. Okay. Now, in the plastic analysis, why you require these magnitudes is the bending moment is maximum, say their plastic hinge will develop first, then slightly lesser value second plastic hinge, then third plastic hinge, like that. To know the sequence of plastic hinges, in what sequence plastic hinges will form, we must know what are the magnitudes of the moments. Then you will know where first will form, where second hinge will form, like that. So now that's why I have given you positive bending moment, negative bending moment. If at all the beam is subjected to central point load, they are equal. So this is the information for the fixed beam subjected to central point load. Now let us see fixed beam subjected to UDL. Now, second one is fixed beam subjected to UDL. Uniformly distributed load. Small w, kilonewtons per meter, A, B. Now this also we know the fixed end moment. MA is equal to WL square by 12. MB is also WL square by 12. The deflected shape of the beam, elastic deflection, here slope is 0. This is a deflected shape of the beam. Again, as in the earlier case, here also, if you draw the free bend moment diagram, we know a simply supported beam subjected to UDL. Bend moment is like a parabolic curve, its magnitude is WL square by 8. This we call it as free bend moment diagram. Free bend moment diagram means bend moment diagram assuming the beam as simply supported beam, like this. Next, end moment diagram plus end moment diagram means MA and MB are equal because of the symmetry of the structure, symmetry of loading. So, bend moment diagram due to end moments is a rectangle. So, this is MA, its value is WL square by 12. Even if you have forgotten also, if only one line, positive area is equal to negative area, we can get what should be the value here. This is bend moment diagram due to fixed end moments. Next, from the principle of superposition, final bend moment diagram will go something like this. First positive bend moment diagram like this. Then on that itself you superimpose like this. Area that didn't get overlapped is this much area, and this is positive area, this is negative area. This it got overlapped, so they get cancelled. The area that didn't get cancelled is this much area. Okay. Now, this value is WL square by 12. This is also WL square by 12. And this is, see, WL square by 8 minus WL square by 12. That is the net odd net minus WL square by 12. You will get WL square by 24. This is your final bend moment diagram. Okay. Now, to get again the values, here itself I will write note 1. To find MA and MB, positive area is equal to negative area. Positive area, when you have a second degree curve parabola equation, 2/3 base into height must be equal to negative area is MA into L is also equal to MB into L. So, you will get MA is equal to MB is equal to WL square by 12. That is the first observation. What is the second observation? Maximum positive bending moment is WL square by 24. Then maximum negative bending moment which develops at the supports WL square by 12. What we can say about the magnitudes? So, maximum negative bending moment is 2 times maximum positive bending moment. Earlier, maximum positive bending moment is equal to maximum negative bending moment. Here, negative bending moment is 2 times more than positive bending moment. So wherever you keep the loads, generally when supposing that if UDL is there, negative bending moment is 2 times more than positive bending moment. If central point load is there, positive and negative bending moments are equal. If at all eccentric load is there, negative bending moment will be more, one of the negative bending moments. We will see that case after this is over. So these are the 2 points we have to remember, how the values have come. Next, let us see the third one, fixed beam subjected to eccentric load. Fixed beam subjected to eccentric point load. Now let us see what we have studied. This is eccentric load W, this is A, B. SM you have studied, this point let us say A, B. Fixed end moment at A is W, A, B square by L square. Fixed end moment at B is W, A square B by L square. Again the deflection profile is like this. Okay. Now, same analysis if you make it. Free bend moment diagram if you draw, the bend moment is maximum under the point load. This value is WAB by L. This is positive. Okay. This is free bend moment diagram. Then to this if you superimpose the negative bend moment diagram, because the load is nearer to the support B, negative bending moment at B is maximum. The influence of W on this fixed end moment is more because it's very nearer. That's what you have studied in the simply supported beams also. Here you see under the point load, if load is nearer to the support, reaction is also maximum, WA by L, right, in the simply supported beams. So if a load is nearer to a particular support, his influence on the support will be more. Okay. So far end, because it's too far, influence will be less. Supposing that the earthquake epicenter is at one location, earthquake is there. At that near to that intensity is very high, earth will shake like anything. Far off, if you say 100 kilometers or 200 kilometers, the influence of this earthquake there, simply earth will shake and keep quiet. So here also same thing, the influence of this load at far end will be very little. Okay. So plus end movement diagram. Now two unknowns are there. MA value is less, MB value is more, because it is too far off location. MA is less because of that. So this is bending moment diagram due to fixed end moments. Now if you add the two diagrams, the final bending moment diagram will go something like this. This value minus this area plus minus. So the area that didn't get overlapped is here, and this is Positive area that didn't get overlapped is this one, like this. This value you will get W A B square by L square. This is W A B square by L square. And linear interpolation, if you write it, some expression you will get it. We are not interested in that. So maximum positive bending moment you will get here. But if you see the magnitudes, if at all A is greater than B, maximum negative bending moment will occur here. Slightly less is this one, positive bending moment. Slightly less is this one. So in the order sequence of magnitude, if you see maximum, slightly less, further less. So if at all when you load it, go on loading it further, first plastic hinge will develop at maximum bending moment location. When you load it further, second hinge will develop here because next magnitude is this one. Load it further, third plastic hinge will develop at A. Then mechanism will form. That analysis in the mechanism formation, that means in the collapse till collapse condition when you are loading it, in what sequence plastic hinges will develop, to know that these ordinates are important for us. Not only elastic analysis, plastic analysis also this understanding is required. And strength of materials also this analysis is required. Because from say SM only we have taken here, this we will take up in the plastic analysis also. Okay. Now to find, now is MA we don't know, MB we don't know. Then two compatibility conditions we have to develop. Earlier problem, because MA and MB are equal for the two cases. So one compatibility condition, you drop a tangent, then angle between the two tangents is 0. So at A if you drop a tangent, it will go like this. At B drop another tangent, it will go like this. So angle between the two tangents is 0. So positive area must be equal to negative area. Then second condition is the BB dash. When you drop a tangent, tangent passes through B. That means the deviation is not there. BB dash is not there. If at all theta A is there, then I draw a line like this, then BB dash is the deviation. Now the BB deviation is also 0. So that is the second compatibility condition. Those two compatibility conditions, that means ds in this case static indeterminacy is 2. Two unknown moments you cannot find by using equations of equilibrium. So we have to go for the two compatibility conditions. In SM, all the problems that you have solved, ds is only 1. That's why in simple stress and strains or flitched beams or the uh, cylinders, thin cylinders, wherever you take it, ds static indeterminacy is 1. So you have developed only one compatibility condition. You have a fixed beam subjected to axial load, say. What is the compatibility? Elongation in AC is equal to contraction in CB. Then flitched beams, ds is 1. That means static indeterminacy is 1. Then one compatibility, what you have taken? Because steel and wood beams are rigidly connected and loaded, both will bend to the same radius of curvature. So curvature in wood is equal to curvature in radius of curvature in wood is equal to radius of curvature in steel. So from that you get bending strain in steel is equal to bending strain in wood. So one compatibility when you get it, you can analyze. Two unknowns you can find. Then wire wound thin cylinders. A thin cylinder, if you wind a wire, thin wire, static indeterminacy is 1. What is that? Stress in wire, stress in cylinder. So two unknowns are there, but only one equation of equilibrium, sigma by 0. Another equilibrium equation you will get it. Circumferential strain in the wire must be equal to circumferential strain in cylinder. Wire wound cylinders means to effectively utilize the cylinders, wires are wound because when the fluid flows through them, to avoid the bursting of the cylinder, you will wind the wire. So before fluid enters, the cylinder is under compression. Now when fluid enters, the tension will develop, but net stress will be very less. So cylinders will not break due to hoop stresses. So all such each chapter one compatibility condition you have used, and here only here you have to use two compatibility conditions. Theta must be 0, that means angle between two tangents. Deviation also must be 0. Then ME and MB you will get. Let us see how to get them. to find MA and MB. First you have to use from Morse theorem 1. Theta is equal to angle between two tangents. Angle between two tangents drawn at A and B is equal to A by EI is equal to 0. So positive area is equal to negative area. Then from Morse theorem 2, delta is equal to BB dash. What is BB dash? Deviation of B away from the tangent, away from the tangent drawn at A is also 0. BB dash is 0. B at A is nothing but A x bar by EI. This also 0. So A by E is 0, A x bar by EI is 0. If areas are equal, then to make the moments also equal, centroids must be on the same vertical line. This is positive area, negative area. They should give same moment. Otherwise, sum will not be 0. This is a W AB by L here, this value. This is the CG of the area, let us say. Somewhere here it is lying. The negative area bend moment diagram, the CG must be in the same vertical line. So that x bar of positive area, x bar of negative area must be equal. Then positive area into x bar by A, negative area by A into x bar will be equal. So to satisfy that Morse theorem 1 and 2, the bending moment diagrams, positive area and negative area have no choice. CG of the positive area by EI, CG of negative area by EI must be on the same vertical line. So that x bar must be equal. So from this and this is one condition. X bar means from here if you measure MB plus 2MA by MA plus MB into that x bar uh, into L by 3. That is what is the CG of the trapezium. A plus 2B by A plus B into H by 3. So from that condition you will get one more equation. Positive area is equal to negative area, one equation. X bar value of this, X bar value of this. One more equation. Solve them, you will find the MA and MB. Solving 1 and 2, MA you will get W A B square by L square, MB is equal to W A square B by L square. This entire, so how to solve the two simultaneous equation solving, any textbook will give us. Again, entire story we don't have to write. Next, second point. This I think maximum positive bending moment, maximum negative bending moment is at B. Maximum negative bending moment at B. Bending moment is at B. Why? Because load is nearer to support B. Whichever support the load is nearer, there you will get WA square B by L square. There you will get maximum negative bending moment. Next, minimum moment. That means minimum negative bending moment is at A. WAB square by L square. Then maximum positive bending moment will take intermediate location. Sequence is like this. Sequence. In this we can write the ascending order. Ascending order of bending moments. First is MA is less than MC is less than MB. You can say like this, MA less, less than MC less than MB. Or simply you can write MA, MC, MB. MC means here, moment at C. Minimum, slightly more, slightly more. That means maximum. Okay. Now, now when you load it in the plastic analysis, if you load it, first plastic hinge is at B. Load it further, second hinge at C. Load it further, third hinge at A. B, C, A, and it will collapse. Okay. So that order we will see again in the plastic analysis of structures. Fourth one, let us see a fixed beam subjected to a central moment M. This is a most standard case here also, A, B, C. This distance L by 2, L by 2. Now, due to this moment M, the reacting moments also clockwise. MA you will get M by 4, MB is also M by 4. Clockwise only will get because of this reason. This purpose, as I told you, MA, MB purpose is not to balance M. Their purpose is to make the slope 0. In the process of making the slope 0, applied moment, reacting moment, same direction you will get. We will see the deflected shape, then you will know why it is developed in the same direction. When I turn it like this, the deflected shape will go something like this. See how my fingers are moving. When I turn it like this, see fingers are going right side down, left side up. So accordingly it will deflect. This goes down, that goes up. Now to determine the directions of the movements, what we do is to find directions of MA and MB. First permit the slopes to happen. That means like this. Take a simply supported beam, apply the moment M. Then how it will deflect? When I turn it like this, it will deflect like this. This point, let us say A, B. This is theta A. This is the deflected shape of the simply supported beam when a moment M is applied. Now what fixed supports must do is, now this is a fixed support here, fixed support here say. What is its task? Its task is not to balance M, but to make the slope 0. Now you see, since you applied clockwise, if the reaction is anti-clockwise, then theta A will increase. But actually purpose is to make the slope 0. For the slope to become 0, this fixed support must go here and press him down. Like this fellow should press him down. And here also, if this is clockwise, it has to be also clockwise, you see. You have to press him up like that. Then only theta will become 0. Now in the process, you see, reaction, MAMB, applied moment, all of them are in the same direction. Then who will balance? Then supports will come into picture. They will offer an anti-clockwise couple. Finally, the beam will be completely in equilibrium. So that's the reason why. Why it is M by 4? We will see later how to prove that after moment distribution method is over. After you understand it, within 5 seconds you can derive how that m by 4 comes. Okay. So now when you draw the Bend-Newman diagram, final Bend-Newman diagram, if you try to draw directly, now you see m by 4, m by 4, total is 1.5 m, 1.5 m clockwise. To balance it, anti-clockwise couple should develop like this. So VA you will get 1.5 m is the total moment by L. Now VB is upward, 1.5 m by L. Now you see completely it is in equilibrium. Now if you draw the Bend-Newman diagram, it will go something like this. What's the Bend-Newman at B? Exactly right side of B, Bend-Newman you cannot calculate because it's in air. So not defined. At B there is a couple. Again you cannot find. And exactly under couple bending moment is indeterminate. Now you have to stand here. Look right side. Section right side clockwise. It will hog. So you have to write it as m by 4. Next, bend moment at C you cannot find. You can find bend moment at RHS of C here. Stand there, look right side. You have two forces that you have to find. So you will find that bend moment at RHS of C. What you have to do? First you have to go and stand. Stand at RHS of C and look right. What you will get? Plus VB, that means plus upward forces will give positive endowment, plus VB into L by 2 minus MB means M by 4. So 2 means 0.75, 0.25. So you will get M by 2. So this is M by 4. At RHS of C you will get M by 2. Now at LHS of C if you want, stand here. Now look right side. When you stand at LHS of C and look right, this M also will come. This big curve, though you have done such a big curve, actually it acts at C like a point moment like this. So you don't stand at C, you stand here first. Then don't stand at C, then stand at LHS of C. Stand here, now look right side, now you can see that moment. If you stand exactly at C, then you don't know whether under your leg how much movement is there. It should be visible. So bend moment at LHS of C. If you want to find bend moment at LHS of C, what you have to do? First go there and stand at LHS of C. Stand at LHS of C and look right. Don't want? You can look left also. You will get three forces now. Plus 1.5 m by L into L by 2. Same distance because that is very 0.01 mm. Upward force is positive bending moment. So VB into L by 2. One is over. Next, section right side clockwise hogging. So minus m by 4. Next, section right side, this is also hogging, minus m. So you will get minus m by 2. So bend moment at LHS of C, you are getting minus m by 2. That means it suddenly changes to this position. Then here, bend moment at RHS of A. Stand here, look left. Section left side clockwise. It will sag. So this is positive. This is m by 4. So now your bend moment diagram will go something like this. This is minus, plus, this is plus, this is minus, plus, minus. Okay, this is your bend moment diagram. How many points of Conrad flexure are there? Number of points of contraflexion in this case are 3. 1, 2, 3. 3 places when moment changes its sign. That means fixed beams for all types of loading, the number of POC are not 2. See, point load is there, UDL is there, number of points of contraflexion are 2. But if a moment is there, number of POC will become 3. For any problem, even if you take a cantilever beam, you might have learned that in a cantilever beam number of POC are 0, but that is not correct. Any problem, any beam you take it, points of contraflexion will depend on what type of loading is there on the beam. See, cantilever beams you have studied that almost all problems, there is no point of contraflexion at all. But you see, if I take a cantilever beam like this, a moment some M I apply, here I apply 2M, then some other moment I apply here like this. Then what will happen? Bend moment diagram. See, section right side anti-clockwise positive plus M up to here, then 2M goes like this, then this minus M, it can go up to here, like this it can come, like this. This is a possible bend moment diagram. So, number of POs is 1, 2, 3. So, number of POC depends on the type of loading. In the exam, this is general loading. Number of POC in a cantilever beam subjected to general loading is the question, let us say. Number of POC in a cantilever beam subjected to general loading are 1, first option is 0, 1, 2, none. Then none you have to answer. It can be anything depending on the type of loading, or if they give none, it will be an extremely difficult question. D option will be it depends on the type of loading. If they give say, then depends on the type of loading you have to answer. It is not 0, it is not 1 or 2, it can be anything, it depends on the magnitude of or type of loading that the beam is subjected to. Okay, you must, that's why in the exam you must carefully see the wording. What he is asking, you for that only have to answer, not what you know. Okay, so you see, cantilever also we made 3 POC. It can, I can make 4 also, I can make 1 also, I can make 0 also, depending on the type of loading. That's why in the fixed beams subjected to downward loading, POC are only 2. If you have a moment, it can be 3. As you have seen here, number of POC are 3. So number of POC is a function of type of loading. Clear? Now let us see fixed and how the numericals come. Fixed end moments are, they give you the beam and assume that I values are different. Okay. Now this point A direct will take say B, C, D. This value is say 2i, this is say I, 2i. And at B there is a moment of m0. This is anti-clockwise moment m0. Okay. This from here to here, let us say this distance is L by 4. This is L by 2. This is L by 4. In the trusses chapter, I gave you one point. If a statically determinate structure is subjected to a system of forces which are already in equilibrium, support reactions are 0. Now, this is not a statically determinate structure, it is a statically indeterminate structure subjected to a system of forces which are already in equilibrium. But still the reactions will develop because the fixed end moments etc., those reactions purpose is not to keep them in equilibrium but to make the slope 0. Now let us see what it means is this one. Here itself we will write. To find the directions of MA and MB, directions of MA and MB. First permit the slopes to happen. This is the beam, let us say. This point, let us say A, D. Here moment is m0, here moment is m0. This is L by 4, L by 2, L by 4, B, C. Now it is a statically determinate structure subjected to a system of forces which are already in equilibrium. For such cases, V and Vd are 0. V is 0, Vd 0. That's what you have learned in SM also. Now when you draw the bending moment diagram for this one, it will go something like this. Between D and D, C and D, bending moment is 0, 0 here. Move your fingers up to right hand side of C. Stand there, look right side. No load, so bending moment is 0. Now at LHS of C, stand here, look right side. M0 suddenly appeared. So up to here it is 0, suddenly it goes up to M0. Now it is constant up to here. Now here it is 0, up to here it is 0 only, like this. M0. This is positive bending moment diagram. This we call it as free bending moment diagram. Because of this one, what is a deflected shape? Strength of materials you have studied, any segment of a beam, if bending moment is 0, it will not bend, but it can rotate. It will remain as a straight line and rotate. So, up to, because bending moment is 0, it must remain as a straight line like this. Here also it must remain as a straight line. Why downward? Why can't it be upward straight line? Because it must sag. To facilitate this BC member sagging, these two segments must come down like this. See here, then only I can draw a smooth curve like this way, right? This is straight line. This is also straight line. Now you see theta A now clockwise developed, theta D clockwise. Fixed to find directions of MA and MD. Okay, now what's the purpose of the fixed end moment? Now when you fix it, its purpose is to make the slope 0, so it must press him up like this. Here also when you have a fixed support, its purpose is to press him up like this so that theta becomes 0. So even this structure is subjected to a system of forces which are already in equilibrium, still fixed end moments will develop to make the slopes 0. So you will find that MA will act like this, MD will act like this. So first point that you should understand is that there will develop MA and MD. To confuse you, what they give you is because they are in equilibrium, fixed end moments are 0 they give. Then you should not put them as 0, you have to confirm. Now itself you are confirming. That's why I told you for all general cases I am telling. Determinate structures, system of forces which are in equilibrium, no reactions. Indeterminate structures, even if it is subjected to system of forces which are already in equilibrium, there will develop fixed end moments or there will develop reactions. Because in this case, fixed end moments purpose is not to balance the m0 to make the slope 0. Then how to be in equilibrium? Some other reactions, support reactions will take care of the equilibrium aspect of the structure. Okay. So MA and MD, now that you have understood, they have to be there. Now draw the Bend-Newman diagram. This is a 2 marks question. You must finish off in 1 minute time. Now free Bend-Newman diagram, first you have to draw like this. This ordinate is M0, M0, positive. This is called free Bend-Newman diagram. Free. Then end moment diagram, that is completely negative. From here to here we have to draw. This is minus. This is MA, this is MB, MD. But they have to be equal. But in this zone it is 2I, I, 2I. If you superimpose these two diagrams, it will become something like this. The negative Bend-Newman diagram will go like this. The positive Bend-Newman diagram will go like this. So the area that got overlapped is this one, that didn't get overlap is this point, minus, plus, minus. Okay, number of pivots you will get in this case are 2. This is final BMD. But our task is to find MA and MD now. Positive area by EI must be equal to negative area by EI. Now to find MA and MD, because EI is not constant, you have to write like this. Positive area of Bend-Newman diagram divided by EI must be equal to negative area of Bend-Newman diagram divided by EI. So positive area, so M0 into L by 2, this is a positive area, divided by EI must be equal to negative area. Negative area is split into two rectangles, MA into L by 4, MA into L by 4 by E into I means 2I. So you can write this as like this, MA into L by 4, extreme left side rectangle area by E into I means 2I. This type of segments too are there, left and rightmost point plus central one, MA into L by 2 central area by E into I itself. So you will get MA is equal to MB is also same, 2 M0 by 3. In 2 minutes time you must finish off this task. Quickly you should recollect that there will develop fixed end moments, then positive area by EI must be equal to negative area by EI. Then I think you must have been taught more lectures on how to draw Bend-Newman diagrams. So this is simple case. Quickly we should draw such Bend-Newman diagrams. We should not think Bend-Newman data RHS of D, LHS of D, that story you write for SM. Having understood that, next time when you are doing by inspection itself, you should be able to draw the Bend-Newman diagrams. Otherwise, drawing Bend-Newman itself, if you take 10 minutes time, say, then where the question of finding the positive area, negative area, you think within 1 minute time, impossible. Okay, see number of POC here, you see, how many you will get? Only 2. Number of points of reflection are 2, and that too they will develop at the point of application of the moments. So this is our task. Next.